Thank you for joining me. I'm glad to have you here. I want us to look at energy stored in a capacitor. And of course, in our previous lesson, we discussed that a capacitor is just a device for storing up charges or for storing up electricity. Okay, for notes on the definition and some calculations under the definition of capacitors, check the link below. Now, today I want us to look at energy stored in a capacitor. And here we have a picture of what a capacitor is all about. Assuming we have this as a capacitor, now it is connected, assuming this is a key, from here it is connected to, let's say, a potential difference V. Remember here, this one possesses charge. These are two equal but opposite charges. Let's say this one possesses negative charge and this one possesses positive charge. Now, by energy stored in capacitor, we want to look at how we can maybe use this potential difference here to charge here, or use this whatever energy we have here, can use it to charge here. And by doing that, we need to do some work. Now that work we'll do there is, assuming this is a charged plate and this one is an uncharged plate. Now if you want to charge this one, that means we need some work, we need to do some work to move charges from here down to this plate that is uncharged. That work that we need to do in order to carry charge from a charged plate to an uncharged plate to store it there is what we refer to as energy stored. Now, work done, in other words, we can now say that yes, work done is equal to the potential difference here. Reason, this one, before you start charging, of course, charge will move from this one that is at 0, maybe to this one now that is a charge, Q. And by so doing, potential difference will now move from charged to uncharged. Therefore, at this point, we now regard that charged one as moving from 0, like to move from 0 to the uncharged one, V. In other words, we can now have that work done is equal to the average potential difference, average PD times this charge here, that the one we are trying to move. Okay, now when we say average PD, it will now give us that work done is equal to the average, which is, of course, you started from initial up to the final potential V. So it will now give us half potential difference times the charge. Now when you do that, we have that work done is equal to half. And of course this one is 0, you don't need it. All you need to do is half V. Half V times Q. We can label this one as our equation 1. This is the work done. Now we now have work done is equal to that. But before we proceed, remember, recall that charge is equal to CV. That is the first one. We can call this one A, equation A. If you make C the subject, C will now give us Q over V. We can say this is B. If you make V the subject, V will give us what? Q all over C. We can call it C. Now, there are two variables here, V and Q. In the first place, I can say put the value of Q here. Now by so doing, we now have A. Now we say substitute the value of A into equation 1. Put this into this. When I have that work done, when I give us half V into Q. Q will give us CV. And it will now give us that the work done is equal to half C first, then V times V squared. This is the second equation. This one has V here, and of course C. We can say substitute equation C into equation 1. That is where wherever we see V, we put this. So we are going to have work done is equal to half. In place of V, we put Q over C. So we now have, we can put it in bracket, Q over C, multiplied by Q times Q. Now if you open this bracket, you now have that work done is equal to half Q times Q squared. So now give us a Q squared all over C. Now this is equation 3. Remember we said that yes, that work done in moving an uncharged plate to a charged plate is the energy stored in the capacitor. Therefore, we cannot say work done is the same thing or is equivalent to energy stored. So in most books, you will see this as work done is equal to this, or you can see it as energy stored. In other words, we cannot have all these. We can put them together. This one, the first one, we can have that energy stored E is equal to half QV. This second one, we can have it as energy stored is equal to half CV squared. The third one, we can have it as energy stored is equal to half Q squared over C. So these are equations for energy storage. Having done this, let us take one or two calculations to buttress what we have said so far. Okay, we'll take this. This question before us here, please pay attention. This question says, we have a diagram, a circuit diagram before us, and they said a capacitor of 10 microfarad. And of course, this is the capacitor here. This is the potential difference. Only just to these two parameters given to us. A capacitor of 10 microfarad is connected across a cell of 12 volts, as shown in that diagram. Calculate the energy stored in the capacitor. And of course, the answer must be among these options here. Solution. Now, from here, we can have that, of course, this is C, this is V. So C is 10 microfarad. Remember, microfarad is 10 to the power minus 6. So we have 10 times 10 to the power minus 6 farad. V there is 12 volts. Now, these are the three equations we have, and from these three, only one will go. Of course, the only one that will go is the second one. And this one says E is equal to half CV squared, which will give us half times C. C, instead of using this, we use it. Anytime you see micro, please make use of it. Unless maybe from the question, from the options, the micro is indicated. If not, insert it. So which will now give us 10 times 10 to the power minus 6 times V. V is 12. Remember, V is squared. We put our square there. Half times 10 times 10 to the power minus 6 times square of 12. Just times 12 is 144. We have 144 here, which will give us half times 10. 10 times 144 will give us 1440 times 10 to the power minus 6. Now, half times this, half times 144 will give us 720. 720 times 10 raised to the power minus 6. This is not in standard form. We put it in standard form. If we put it in standard form, of course, this is 720, and there is point here. If we move our point into 2 places, we reduce this by 2. If we move towards the right, we increase by 2. So we are moving it. So we have 7.20 times 10 raised to the power minus 4 joules. And of course, from every indication here, we now have that energy stored in this capacitor is option B. Okay. We have this number 2 question. We have this diagram for us. Now, if you look at this diagram, this is parallel connection. Because it's a parallel connection, the whole arrangement is connected to 100 volt supply. So we have that in the circuit above, the potential across each capacitor is 100 volts. The energy stored in the 2 capacitors is dash. It must be one of these options here. Now remember, this is a parallel plate capacitor. And for a parallel plate capacitor, we have this. This one stores its own charge. This one stores its own charge. So in other words, we now have energy stored. Total energy stored here is energy stored in the 2 microfarad capacitor plus that in 3 microfarad capacitor. Okay, so how do we do that? We have energy stored in 2 microfarad capacitor. We can say E2. E2 is half CV squared. E2, we are referring to this one, which will now give us half times the capacitance here is 2 times 10, remember it's microfarad, times 10 raised to power minus 6 farad, times V. The V there is 100. Remember, it is squared. Because it is squared, we have E2 is equal to half times 2 times 10 raised to power minus 6 times 100 squared. And of course, if you press your calculator there, 100 squared is 10,000. You can pause this video and then take your notes one after the other. So which will now give us energy stored in the 2 microfarad capacitor is half, and of course I will take everything at the same time from here. I will take everything. Half times 2 is 1. 1 times 10,000 will give us 10,000 times 10 raised to the power minus 6, which will give us 1, 2, 3, 4. 1.0 times 10 raised to the power minus 2 joules. Energy stored in the 2 microfarad capacitor. Now this is the first one. Now second stage, energy stored in the 3 microfarad capacitor will give us E3. E3 is the same formula with this, half C. Of course, we can say here 2 here, half C3 times V squared, which will give us half times C3, which is a 3 microfarad, 3 times 10 raised to the power minus 6, times that of V. V is 100. Remember, 100 squared. Now, we'll come back here and say E3 is equal to half times 3 times 10 raised to the power minus 6 times 100 squared. The 100 squared will give us 10,000. I'll take everything. E3 will give me half times 3 is 1.5. 1.5 times 1 times 10,000 will give us 15,000 times 10 raised to the power minus 6. At the end of the day, I will have 1.5 times 10 raised to the power 1, 2, 3, 4. If you count 4 like this, you subtract 4. And if you remove 4 from here, we'll now have 2 joules. Therefore, the total energy stored in the two combinations, total energy stored will give us E2 plus E3, which will give us E2, remember this and this, E2 is 1.0 times 10 raised to the power minus 2 plus 1.5 times 10 raised to the power minus 2. Everything will give us 1.0 plus 1.5 will give us 2.5. Remember our law of indices. Since they are of the same power, you pick 1 times 10 raised to the power minus 2 joules. And of course, this is the final answer. And it corresponds to option C. So option C is our correct answer. Now we have this question here, and this question says we have capacitors P and Q of capacitance 2 and 4 microfarad connected in parallel to a DC source V. Now here the question says the diagram shows 2 capacitors P and Q of capacitance 2 and 4 microfarad respectively connected to a DC source. The ratio of P to Q is dash. The ratio of energy stored in P to Q. The ratio of energy stored is missing. Energy stored in P to Q. Now, solution. There are 2 capacitors there. Now we'll take the energy stored in each of them because 2 of them will not store energy at the same time. They store energy according to their capacities. So we now have energy stored in P, which is EP. Energy stored in P is EP, which is half CV. You can put P here squared, which will give us EP is equal to half times CP. CP is 2. 2 microfarad, 2 times 10 raised to the power minus 6 farad times V. Since, and here, the value of V there is V. We put it there as V squared. Now, we can keep it there, or we can continue and say EP is equal to half times this will give us 1 times 10 raised to the power minus 6 V squared in joules. Next step will now be energy stored in a Q, which is EQ is equal to half C, we can put Q here, CV squared. And it will give us that EQ is equal to half times C. For the Q, C there is 4 microfarad times V squared. V there is V, so it is squared. Now, which will now give us EQ is equal to half times 4 is 2 times 10 raised to the power minus 6 joules. We have found the energy stored in P and energy stored in Q. The question is the ratio of energy stored in P to Q. See, they say P to Q, that means the ratio is equal to P to Q, P over Q. That is the ratio of P to Q. Which will give us energy stored in P is this 1 times 10 raised to the power minus 6 V squared all over energy stored in Q. Energy stored in Q is 2 times 10 raised to the power minus 6 V squared. Let's see the things that will cancel out. In the first place, V squared can cancel out V squared. This one can cancel out this. and we have what is remaining is 1/2. Then we can now say that, therefore, ratio of energy stored in P to Q is 1:2. And 1:2 is option D. Okay, the last but not the least question. Now, we have this question here that says, the energy stored in a capacitor of capacitance 5 microfarad is 40 joules. Calculate the voltage applied across its terminals. Now, this one is very simple. They gave us C to be 5 microfarad, which in turn give us 5 times 10 raised to the power minus 6 farad. Energy was given to be 40 joules. They said calculate V. Now, since we are looking for V, V will give us, from the relation that says E is half CV squared. We'll now have, we substitute. If we substitute, we have E 40 is equal to half times C. C is 5 times 10 raised to the power minus 6 times V squared, which will give us 40 is equal to half times 5 will give us 2.5 times 10 raised to the power minus 6 V squared. At this point, we make V squared the subject at this point. So at this point, we now have V squared is equal to 40 divided by 2.5 times 10 raised to the power minus 6, which will give us, don't just press calculator, you can send this one, you can send it up, but from law of indices, which will then give us 40 times 10 raised to the power. And if this one goes up, the sign will change to positive, all over 2.5, which will now give us that V squared is, we'll now have 40 divided by 2.5. And it will give us 16. So we now have 16 times 10 raised to the power 6. V itself will give us the square root of 16 times 10 raised to the power 6. And we will now have 16 times 10 raised to the power 6. The square root of that will give us, for square root of this, V will give us 4,000 volts. Okay, that is the PD applied to that terminal. Alright, this is where we draw the lesson to an end. Feel free to contact me anytime for any lesson. I am here to assist you. If you find this lesson interesting, please like, share, and then subscribe. If you have not subscribed to this channel, subscribe so that the next lesson you will be informed. Thank you.